All right, hello everybody. We're going to talk about lecture 4.3 today, which is on row space and column space. So let's start off. We have a matrix A that is n by m rather. So it does not have to be a square matrix, just n by m. So you have n rows and m columns. Okay. What we're going to define, we know that you can look at the row vectors as a collection of vectors. And if you take their span, so if you take the rows of A as vectors in Rm, and you take their span, we're going to call that, well, we're going to abbreviate it as row of A, and we're going to call that the row space. All right, so you can form a subspace of Rm, right? This is a vector subspace. And we know what subspace means from section 4.1, right? It's inside of Rm, it contains 0, and scalar multiples and sums of guys in the subspace belong to the subspace, right? You can't escape the subspace with those operations. And it's a subspace in the space that holds the vectors, which have m components, so it's an Rm. Likewise, we could take the columns of A, right? So you can do that. Those are in Rn. We're going to abbreviate that as COL of A. And guess what? We'll call it the column space. Oops, column space. And that's a vector subspace of Rn. Right, so first and foremost, the row space and the column space typically have nothing to do with each other, right? In fact, they don't even have to be in the same vector space, right? So you can't really say the row space and the column space are the same, right? First and foremost. However, there's going to be a definite connection between the two in terms of dimensionality, and we'll see that as time goes on through the lecture. But to find these, right, so you have these spaces, and we've already have talked about the importance of getting a basis for a vector subspace, right? You'd want the fewest number of linearly independent vectors that span a vector space, the bare bones, if you will. And so if I want to find the bases for either of these using the matrix A, right? So you don't ever want to have to create something new. You want to start with what you have and ask the question, what can I do to this to determine what I want? All right. And so to answer the question, to find a basis for the row space, so for this guy, for that span of those vectors, all you want to do, guess what, is put A into echelon form, as we always do anymore, and simply use the non-zero rows as a basis. Plain and simple. So whatever A is in terms of an echelon form, all the non-zero rows taken as a collection of vectors is a basis for the row space. Okay. And if you want to do the same thing, but for the column space, right, so that's for the row space, pen's already running out, to find a basis for the column space, again, put A into echelon form. And this time we're going to identify the pivot columns, any column that contains a pivot. Remember, and pivot is leading the first non-zero term, right? So identify the pivot columns and go back to A and use the corresponding columns as the basis. So that's one little difference here. With the row space, you don't have to go back to A. You simply can use the rows that you end up with in the echelon form to form your basis. For the column space, once you identify the pivot columns in the echelon form matrix, you have to go back to the original A and just identify the corresponding columns to those guys and then use that as your basis. So just be careful here. You have to go back here where you do not for A, for the row space. What we can say, and this follows from what we've already have done, is that the dimension of the row space is equal to the dimension of the column space. All right. And so we're going to use that fact. So even though they don't necessarily have, they're not the same subspace. In fact, they're generally not because they're in different spaces. We do know that the dimension of each of them, which is the number of vectors in a basis. So if you take the number of vectors used here and the number of vectors used there, those numbers have to be the same no matter what matrix you take. All right, so let's use that and do a couple of examples. Let's put this here. Just take care of my notes here so I don't get them scrambled up. Sorry about that. Monday for me, moment, I'm not quite awake yet. All right. So here, all right. So we have, just keep up here, the dimension of the row space of a matrix is equal to the dimension of the column space. And we're going to call that the rank, right? So that common number is the rank of A, right? So any matrix A has a single rank. That rank is given by either of those two equal numbers. All right, and if you take the null space, you'll say, why are you talking about the null space all of a sudden? You'll see why. There's a theorem that we're shooting for in this particular section that connects these two in a very nice equation that's almost a miracle. The null space is the set of all vectors that it's a solution of AX equal to 0, right? And so here, the dimension of the null space is, we're going to call that the nullity. Okay. And so what we're going to be shooting for in a lot of examples, we're going to compute rank, we're going to find bases for the null space, row space, and column space. And then in so doing, we're going to compute the nullity and the rank, and then show if we do a certain arithmetic combination on those guys, you always get the same number associated with the matrix, right? So it's matrix dependent, but that sum will always be computable by something involved in the structure of the matrix. All right, so let's actually just start off and see what happens. All right, so first one, we want to find bases for those three spaces. And so we're going to have to put, no matter what we do, we have to put them in the matrix into echelon form, right? And so we are now experts at doing this, right? So we'll just write down the matrix. And I want to put zeros here and here. So why don't we just add -2 times row 1 to row 2, and -2 times row 1 to 2, 3, and replace those two rows by those guys. If you do that, I won't bore you with the arithmetic again. What you get is this. And 0, 0, -3, and -6. All right. And so now you want to put a 0 here. So what we'll do is we'll multiply row 2. First off, why don't we just get rid of that -1/13? So we'll multiply row 2 by -1/13 and just replace row 2 by it, so I don't have to be using these big numbers. You don't have to if you want to keep it. If you don't want to do it, you don't have to, but I'm going to. And just write down the third row. And now it's easier to see that if you multiply row 2 by 3 and add it to row 3 and replace row 3 by it, you get this matrix where the first two rows are the same, but then the last row becomes a row of zeros. All right, so as what we normally would want to do, let's highlight the pivots for later use. All right, so those are the pivots, leading term, or first non-zero terms in every row, and then the other guys have to be free. You're either a free variable or you're a pivot. All right, and so for the row space, all right, so we had A, where we put into echelon form and we just use the non-zero rows, right, as vectors, as for the basis. So the basis for the row space is just the first two rows. It's the non-zero rows. Okay, easy enough. For the column space, remember what you have to do here is identify which columns in the echelon form have pivots. Well, that would be the first and the third, and go back to the original matrix now. So we can't use that. We have to go back here and use those guys. And so the column space has the basis 1, 2, 2, and 5, negative 3, 7. Okay. And let me also point out here, remember the row space here consists of 3 vectors in R4. So these vectors here are in R4. That's a vector subspace of R4 with dimension 2. Remember, the dimension is the number of vectors in the basis. And the column space is comprised of 4 vectors in R3. It's a vector subspace of R3. Its dimension is the number of vectors in its basis, which is 2. All right, so they have to be the same. Therefore, the rank of A is 2, just by definition. Okay, now for the nullity, remember what you want to do there is in your mind, you're setting on the right-hand side, you're putting a column of zeros, right? Because you're trying to solve. So I'll partition where I need more space. Or actually, let me just go to paper. It's easier. All right, so just fold this. All right. All right, so for the null space, what you're doing is you're solving that system. And so you have a column of zeros over here. And so what you want to do is, we've already identified the free variables. So let's let x4 be s1, and let's let x2 be s2. Remember, we want to rename them just for good bookkeeping. And then we just go through and substitute in. Right, and so from this one, we know that we know how to relate x3 and x4. Right, so x3 plus 2x4 is equal to 0. And so x3 is minus 2x4, but x4 is s1. All right, so I have that. And then it remains to find x1. We know that x1 minus 3x2, and I'm going to put s2 in for x2, plus 5x3, but x3 from the previous one is minus 2s1, and then plus 11x4, but x4 was s1, equals 0. So I'm doing 2 things at once. I'm going through and writing this out in terms of our original variables, but I'm plugging in the values of x1, x2, x3 in terms of s1, s2, so to speak. If I simplify the left side, I get x1 minus 3s2 minus 10s1 plus 11s1 is plus s1 equal to 0. And so x1 is 3s2 minus s1. Okay. And so a solution, all right, so a solution, remember we're solving this. And so this is my vector x, right? The structure of a solution satisfies these conditions on the components. What we do is we plug them in. So plug this in for x1, x2 was s2, x3 is minus 2s1, and x4 is s1. Right, I just plugged in those values for the components. Okay, pull apart the s1s and the s2s. So from the first one, I have a minus 1, 0, minus 2, and 1. That's all times s1. So I pulled out that scalar multiple. Plus, For the S2s, I have a 3 and a 1, 0 and a 0 times S2. All right. And so what that says is that the null space, remember here, S1 and S2 are any real number. And so what that tells you is that the null space is the span of -1, 0, -2, 1, and 3, 1, 0, 0. And in fact, those are linearly independent, right? You can actually show that. And so there is your basis for the null space. And notice that the nullity, by definition, the nullity is the dimension of the null space. That's 2. There's 2 basis vectors in there. So what does that say? Remember, we have the rank of A is 2. The nullity of A is 2. And if you add those, we get 4, which is the number of columns of A. So, I mean, this is just an example so far. Let's actually see if it's true for all these other matrices that we look at. But for now, that's an observation, right? If you add the rank and the nullity of a matrix, you get the number of columns of that matrix. All right. All of these problems are the same, right? So once you get used to the terminology, it's not bad, right? But until you do, you know, it's like, well, what am I talking about? What's row space, column space, nullity, rank? I mean, it's all these terms going around. And it's very easy to get befuddled. That's how we're going to do several examples. So let's look at example 2, find null space, row space, and column space of that matrix. And of course, we're going to find the rank and the nullity again, just to make sure we get to see these relationships in action. So first things first, put A into echelon form. Okay. And so good thing here is I only have to do something to that row to get a 0 in there, because I already have a 0 in that corresponding place in the second. I'm going to multiply row 1 by -5, add it to row 3, and replace row 3 by it. And in so doing, I get 1, 2, 0, 0, 3, 4, 0, -10, and 6. And then I want to put a 0 there. So let's go through. We'll multiply R2 by a third first, and then I want to get rid of the -10, so multiplying the top by 10. Add that to row 3, and replace row 3 by it. And so what I get is the matrix 1, 2, 0, 0, 3, 4, 0, 0, 58 thirds. Yeah, it is what it is. All right, so now you want to identify the pivots. There those guys are. And so guess what? There are no free variables. Great. So that actually simplifies our life considerably for the null space, right? Because what that means is all 3 columns are linearly independent. And so therefore, the only solution to this guy is the 0 vector, right? And so the null space, right, the null space is just the vector with the singleton 0, but that has no basis. Right? There's no way to generate that using a basis element. And so the nullity of A is equal to 0, right? The basis is empty, so the nullity, the number of vectors in the basis, is 0. Okay, now let's go through and do the row space and the column space. The row space has basis. Well, all 3 rows are non-zero. You use the non-zero rows in the echelon form of the matrix. So all 3 of these guys, 1, 2, 0, 2, 3, 0, 0, 3, 4, you write the rows as your column vector. And 0, 0, 58 thirds, those form a basis. So we used all 3 rows there. Given that, we know the dimension of the row space, right, is 3. There's 3 vectors in the basis. that has to be equal to the dimension of the column space. And so that means that if we look at the echelon form of the matrix, every column has to contain a pivot. And indeed it does. Every column has a pivot. So what do? We go back to the original matrix to take those column vectors as the basis for the column space. And so we have 1, 0, 5, 2, 3, 0, and 0, 4, 6. That's the basis. Notice the dimension of both is 3. Okay, so the rank of A is 3. Okay, just so happens that if you add the nullity and the rank, 0 plus 3 is 3. That turns out to be the number of columns of the matrix. All right, so maybe it's true. All right, let's go on to the next example. Let's do a larger one. I mean, we can do this all day long, but we won't. Let's find the same thing. Null space, row space, column space, and we want, in particular, their bases. All right. So let's put the vector matrix into echelon form, right? And so rather than write it again, let's just look up here. I want a 0 there, and I want a 0 there. I already have a 0 there. So I'm going to multiply R1 by -2, add it to row 2, and clunk that into row 2. I'm going to multiply R1 by -1, add it to R3, and clunk that into R3. That gives us the matrix where the first row is the same. Second row is 0, -1, -1, 1, and 2. The third row is changed. It's 0, -2, -2, 2, and 4. And the bottom row is the same. 1, 0, 1, 1, -1, -2. All right, so I have zeros there. Now what I want are zeros here. So what do? Same thing. Multiply the second row by -2 and add it to R3. Clunk it into R3, and then just add R2 and R4 and plug that into R4. Okay. And the matrix that gives us, top 2 rows remain the same, but the bottom 2 rows now become 0 rows. You can check the arithmetic on that. Okay, and so at least now we're in echelon form. Every row has strictly less zeros than the one next bottom or the one after it, and all of the 0 rows are at the bottom. All right, so we identify the pivots. There are the pivots, and the rest of them must be free, no choice. All right, so the row space, let's start with that. The row space of A has a basis that consists of just the non-zero rows, and those are the top 2. All right, so we have 1, 3, 2, -1, -1, and 0, -1, -1, 1, and 2. Notice again, the row space consists of vectors in R5. These are vectors in R5. All right, so this is a vector subspace. This guy, if you took the span of that, is a vector subspace of R5. Just keep in mind where it is. The dimension of the row space is 2. It's the number of vectors in the basis. The column space, well, we have to use the columns in the original matrix that correspond to those that have pivots. Those are the first 2 columns. And so rather than writing it, we're just going to plug those 2 in here. Right? Those 2 as separate column vectors form the basis for the column space. Notice those are in R4, which makes sense. The column space consists of vectors in R4. That's a vector subspace of R4, and there are 2 of them, right? So as it has to be, the dimension of the column space is 2. Right. What that tells you is that the nullity, the dimension of the null space, if the observation that if you add the nullity and the rank, you get the number of columns in the original matrix, if that's to be true, then the dimension of the null space ought to be 3. Well, it is, because guess what? The dimension of the null space turns out to be the number of free variables, right? Because those are the scalars inevitably that we pull out of distinct vectors to write that general form of a solution of the homogeneous system in a nice way. So I will actually let you do this, but notice here we have those three vectors are the free variables. So we're going to call x5 s1, x4 s2, and x3 s3. Okay. Then x2, you just go up here, negative x2 minus x3, which is s3, plus x4, which is s2, plus 2x5, which is 2s1, is 0. And so x2, I'll take the x2 over there, is 2s1 plus s2 minus s3. All right, so I know this much. And the next one's even more fun. You just put x1 plus 3x2, which means you put that whole expression in here, plus x3, or sorry, 2x3, which is 2s3, minus x4, so minus s2, minus x5, which is minus s1, is 0. And so x1 is equal to what you get by taking that to the right side. Notice, and I want you to go through the algebra. There's nothing mysterious about this. You have x1, x2, x3, x4, x5. You have s1, s2, and s3. So you're going to break this into three pieces. S1 times a vector plus S2 times a vector plus S3 times a vector. The vectors you get after you yank out those constants constitute the basis for the null space. And guess what? There are three of them, right? And so indeed, you get the nullity of A is 3. And so if you add those two guys, you in fact get the number of columns. All right. And so this is just kind of a summary of that. We've been noticing this all along, right? And so that is called the rank nullity theorem. Surprise, surprise, it involves the rank and the nullity. But that is always true. No matter what matrix you give me, that has to be the case. Okay, we're not going to prove that, but I think we're pretty much convinced of its validity. Okay, well, that is the main big theorem of section 4.3. So go ahead, give this a go, right? So just practice this. It just involves the same old tools that you've been using all along, but it pulls together some terminology and whatnot. So you want to make sure you get that straight. And then let me know if you have any questions. Okay, take it easy, everybody. See you next time.